Hello everyone, my name is Shashank Gugnani. Today I'm going to talk about the design of a fast, tailless, and quiescent-free object store for persistent memory. So this work was done during my PhD at Ohio State, along with my advisor, who is now at UC Merced. So this is a brief overview of the talk today. I'll first go through the introduction and problem statement. Then we'll take a look at the proposed design and evaluation. And finally, we'll conclude the talk. So persistent memory is gaining popularity in both HPC and data center environments. Persistent memory has memory-like performance and byte addressability with persistence, offering the potential to significantly redesign storage systems. With the recent trend of moving to the cloud, designing a fast and consistent storage system is critical. This is because inconsistent system performance has been shown to directly result in loss of revenue. To give some background on PMEM, PMEM is a new memory technology that is byte addressable. So it provides access to data through CPU loads and stores. Importantly, it retains data across power cycles, so it's persistent. And it is fast, so it provides very low latency. Moving on to the problem statement. Despite its attractive performance, persistent memory is idiosyncratic and hard to program with. Persistent memory can be directly accessed using byte addressable loads and stores through the memory bus. However, the volatile cache hierarchy complicates data consistency and persistence. It may change the order of stores from what's desired and only provides 8-byte atomicity. So data must be explicitly flushed from the cache to be persistent. And these issues result in complex designs for storage systems, which although provide cache consistency, but they often slow performance. So managing persistent memory idiosyncrasies is hard. So our goals in this paper were to provide a system that's fast, so it hides the overhead of persistence of persistent memory and provides close to volatile performance. Secondly, we want to have low tail latency so that we can achieve latency and throughput service level objectives, which are particularly useful for a cloud environment. So overall, our goal is to have consistent and predictable performance. So if we look at prior work, they can be broadly classified into 3 types: uncached, cached, and decoupled systems. Uncached systems do not cache data, so they require complex and expensive transactions on persistent memory, and these compromise performance. Cache systems, on the other hand, cache part of data inside DRAM. And the problem with these systems is that checkpoints temporarily halt system, which compromises tail latency. Finally, we have decoupled systems which use expensive physical logging, or they either don't provide concurrency. So because of these issues, we asked the question, can we design a decoupled storage system that is simultaneously fast, tailless, and quiescent-free? So moving on to proposed design. In this work, we proposed Dipper, a new decoupled multi-level approach to implement fast crash-consistent storage systems. Here we can see an overview of the approach with 3 levels. As we go down the levels, the performance decreases, but resilience increases. So the primary difference between Dipper and prior decoupled approaches is twofold. First, each level contains a full copy of the system, so there is no caching. And second, levels only communicate through shared operation logs. So the word system I used here can be either a single data structure or the control plane of a storage system or the entire storage system itself. And like I mentioned, all levels contain a full copy of the system. Importantly, level 0 represents the front end and is solely responsible for all client requests. So by placing level 0 in DRAM, we can get very good performance. and levels only communicate through shared operation logs, and we'll see how this works later. In this paper, we focus on a two-level Dipper design, which can be used to implement fast, crash-consistent data structures. The intuition is that we have a fully decoupled design with the front end in DRAM and back end in PMEM. We use operation logging on a persistent memory-based log for durability. We use shadow updates for backend atomicity, and finally, observational equivalence for concurrency. So let's see how you can use Dipper to make a volatile key value store persistent with a simple example. So assuming you have a volatile key value store, which is implemented using a hash table and a memory slab indexed using a bitmap, let's see how Dipper works. So first, we have two operation logs inside persistent memory called the active log and the archive log. Second, we have exactly the same representations of the volatile data structures in persistent memory as well. Now let's see what happens when requests come to the system. So if a new request for a put operation comes into the system, we add the operation along with its parameters to the log, and we apply the operation to the front end. And as soon as the operation on the front end is complete and it is added to the log, the response can be sent back to the client. So it's clear that clients can experience very low latency. Now, if a second request comes in, we do the same thing. We add the operation to the log and apply the operation on the front end. And the problem happens when the log is full and a new operation arrives. So what we do in this situation is that we swap the active and archive logs, and we continue operation on the front end without the need to halt. And here we can see that as we're operating on the front end, in the parallel, we can start operating on the back end. So we take operations from the archive log and start applying them to the persistent backend in parallel with the front end operation. Once we're done applying all operations from the archive log on the persistent backend, we can clear the archive log for reuse. Now let's say there's a crash at this point in the system. So we will lose everything inside the volatile domain. Now on recovery, we can recover everything in the volatile domain by first copying data structures from the persistent domain and then applying log operations from the active log. And we have recovered the state of the system to what it was before crashing. So the key idea of this approach is that as long as the update rate for the system is below a limit, the front end and back end operation can be effectively overlapped. So to provide concurrency in the front end, which is extremely important, we use the notion of observational equivalence. The formal definition of observational equivalence is that two data structure states are observationally equivalent if they both give the same answer to any observation from a pre-specified set. So the simple implication of this is that operations which result in observationally equivalent state can be executed in parallel. So in Dipper's DRAM level, we use this approach for conflict-based parallelism as well as pipeline. Conflict-based parallelism means we can have parallel operations on the same data structure as long as they don't affect consistency. Secondly, we have pipelining, which is parallel operations on different data structures, which we can do as long as the conflict order is maintained. So let's see how this works with our previous example. So when two concurrent operations arrive, we add them to the log normally. But since these operations are on different keys, they are not conflicting. Therefore, we can concurrently execute both operations on the front end. So we start operating on the front end, and here we can see that this is an example of pipelining where we are operating on the bitmap and memory slab in parallel. Here we see an example of conflict-based parallelism where we're operating on the hash table in parallel because we're operating on separate buckets. Now, when we apply these operations to the backend, we may apply these operations in a different order. So once we're done applying, we can see that the internal states of the data structures in the volatile and persistent levels are not exactly the same. However, the observable state, which is through get operations, is the same for both the front end and back end. So this guarantee allows parallelism while preserving correctness. So we can operate parallelly as long as the observational equivalence property is maintained. Using Dipper, we propose a new high-performance object store. It provides both key value and file system semantics. So the control plane of this object store is implemented using Dipper, which includes B-tree and other auxiliary structures. For a cost-effective solution, we store data on a high-capacity SSD using the NVMe protocol. An overview of the DStore layout is shown on the right. Moving on to evaluation. We first compared the average latency of DStore compared to other persistent memory optimized storage systems. We can see that DStore provides much better latency, particularly for write operations. This is because the DRAM front end provides fast performance. Next, we compared the tail latency for two workloads, a 50% read, 50% write workload, and a 95% read, 5% write workload. So we can see that DStore has relatively flat tail latency curves, particularly for the write-intensive workload. So we conclude that our decoupled design is successful in reducing tail latency. Next, we performed an optimization drill down to understand the impact of different proposed optimizations. So we started with a baseline implementation that uses an uncached design with physical logging and added optimizations one by one, finally comparing performance with the volatile implementation, which gives us the theoretical peak performance. So from the results, we can see that logical logging and observational equivalence optimizations help in improving the average latency, whereas the proposed Dipper approach significantly improves tail latency. So we find that by successfully hiding the persistence overhead, we can get performance very close to the theoretical peak or volatile implementation. So to conclude, persistent memory is gaining popularity and offers the potential to significantly redesign storage systems. In this work, we proposed Dipper, a new decoupled approach to storage system design. And using Dipper, we designed an object store for persistent memory called DStore, which we showed to be simultaneously fast, tailless, and Quiescent-free. Preliminary results are promising and show that DStore provides much better service guarantees than state-of-the-art storage systems. So with that, I'll conclude and open it up for questions. Thank you.